Good morning and welcome to this webinar also from my side. As Joe mentioned, my name is Sascha Drenkelforth and I'm from TTTech Auto. I'm the tech leader of our consulting business unit, and we support our customers in the design of failure operational system on all levels, be it AD systems, vehicle level, be it X-by-wire or also single ECUs. And today I will speak about the analysis of failure operational architectures and the systematic approach we are taking. And well, is it here? In order to do so, I structured my talk into 5 parts. So first of all, I will give you a very brief intro into TTTech Auto, who we are and what we are doing. Afterwards, I will introduce our reference architecture for 2 purposes. First of all, I will base the rest of this talk on it. And second of all, I can explain some basic design principles we believe in very strongly. Afterwards, I will introduce the safety goals that such an architecture has to fulfill, so any generic AD architecture in general, and how we systematically analyze any architecture under investigation, whether it fulfills those. I will detail the methods and tools we use, and finally, I will conclude with 1 slide on our safety consulting offering. So, TTTech Auto at a glance. Let me jump back. It didn't really work out here. TTTech Auto at a glance, it should be. So, we consider ourselves safety innovation leader. So from cutting edge academic research to series production. And if it comes to series production, that means we have more than 2 million vehicles on the street already with our product MotionWise. We have more than 11 million vehicles in the pipeline to come. We are more than 1,100 highly skilled employees with a global footprint. So we are spread around 12 locations, mainly in Europe, but also in Asia. We have a strong network of OEMs, tier 1s, technology partners, and actually also quite strong shareholders, Aptiv, Samsung, Infineon, and Audi. And maybe most relevant to this talk is that we have 20 years plus experience in safe systems. Offering-wise, it's twofold. We do have products and we do offer services. Product-wise, we offer software products. The already mentioned MotionWise, which is the safety middleware, and also comes with a lot of additional modular products. But also we are offering hardware products. So we are producing small volume ECUs, domain controllers, gateways, etc. in series qualities, but we are also offering testing codes, data loggers, etc. On the service side of things, we do offer integration services for our products, of course, but we also do have an electronic control design house. So we do contracted development of highly complex cutting edge electronics in prototype and in series quality for our customers. And last but not least, we do offer safety consulting. That's the entity I belong to. Having said that, let's get started with the reference architecture. So our reference architecture actually shall answer the question how we get from left to right on that picture. So how do we get from a level 2 system, a fail silent system, to a level 4 system, fail operational one? And if you look at the left side, we do have sensors at the bottom. Those are processed by what we call a main AD function, so a level 2 system. And this one is in control of steering, braking, powertrain, all the actuators. But most relevant, we still have a human driver in the loop. We have this famous fallback ready user in terms of level 3, but in level 2 even in charge. So the driver is in charge and responsible for safety. So moving to the right, to the level 4 system, actually boils down to this one question depicted on the right. How can the human driver be replaced by an electronic supervision and backup system? And one possible answer to that question is our reference architecture, shown on the left. It's also described in more detail in a paper of Professor Hermann Kopitz, who is associated with TTTech. If you look into it, again, the basis of all of that is sensors. But here we need to have more of them. We need to have redundancy. We need to have sensors of different modalities. So we need cameras, lidars, radars, etc., etc. This is being used by the main AD function. It can be the same like the level 2 that allows for good scaling. But next to it, we have two more independent and diverse compute channels. So this human is now replaced by a safety monitor and a fallback. The safety monitor checks the main AD trajectory for safety, non-collision, dynamics, legal aspects, you name it. And if it's not valid, so if it invalidates the main trajectory, the fallback provides an alternative trajectory. It can be a very simple MRA. The safety decision logic on top of that is checking the outcome and the verdict of the safety monitor, and then will ensure that only one trajectory, a valid one, is being transmitted to the actuator level. And on actuator level, we also need some redundancy, because now there is no human driver more, there is no hydraulics anymore, it all needs to be the machine. So we need redundancy. And this architecture has three strong advantages. It allows for strong fault containment units. So each of these boxes can and shall be a fault containment unit. So if it fails, a failure must not propagate to the other ones. It allows for, or it's actually built up for diversity. So you can have diverse operating system, diverse SoCs, diverse algorithms in each of these boxes. And by that, it also helps for any SOTIF related aspects, because the safety monitor, for instance, can check for free space only, whereas the main AD needs to calculate a trajectory. So very different things, very different algorithms, and hopefully they will not see the same edge case at the same time. But we could speak about that architecture for a while, and maybe it's worth an own webinar, but for today, it shall be enough. So let's talk about the safety goals. Which kind of safety goals such an architecture, or actually any AD architecture, has to fulfill, and how we ensure that it fulfills those when we do an analysis. The safety goals are dominated for a fail operational system by now two main kind of safety goals. A system like that one always has to perform the function correctly. So we have two safety goals. We have the safety goal of correctness. Collisions shall be avoided. The trajectory must be valid. And we have an availability safety goal. Loss of function shall be avoided. We always need a trajectory. There's no human anymore, so we always need a trajectory. That also is coined as safety-related availability, SARA. And if you look in our system that are already depicted here, I put on some boxes indicating the ASIL decomposition. On the left side and on the right side. So the nominal functionality with the main AD level 2 system needs to be a ASIL level in ASIL B of D. The same for the fallback AD. It needs to do a minimal risk maneuver in case the main is not available anymore. So it's an ASIL B of D as well for availability. But each of them calculates a trajectory. And each of these needs to be correct. And the safety monitor is checking both for the main AD, because this is nominal functionality, but also for the fallback to ensure that there are no latent faults. So with a quite complex, simple diagram, but quite complex architecture, and we have two different safety goals. And the question now is, how do you check for the validity of this architecture? And we normally start with FSC and TSC reviews. So you see it on the top right. And there we check the general validity of the approach. Afterwards, we are detailing this a lot in systematic analysis on systems, software and hardware level. We do an availability estimation of failure rates in hardware and in software. We identify single point failures or components of identical type. We do check for dependent failures, of course, and we do have formal verification. And each of these methods and how we combine them, I will explain you in a bit more detail in the methodology deep dive. Let's start with the functional and technical safety concept. In the first step, we analyze the architecture for compatibility with the fundamental design principles on a high level, so FSC. moving on to DC. And we check them against the design principles I already introduced. So fault containment units, diversity, encapsulation, etc., with the objective that no single unit must be capable of bringing down the whole system. Fault tolerance is required on a logical architecture level. And redundant channels must not be able to fail simultaneously. So we need strong partitioning. And after this more high-level review of the architecture and the safety concepts, we evaluate this all in detail. So we check for fault containment units, whether they are fulfilled or not, are they diverse or not. We check the whole architecture for simplicity and verifiability, because KISS, keep it simple. We check potential failure modes. So what could go wrong in this kind of architecture, which also will guide all the other analysis we are doing afterwards. We check for scalability. Here it's quite nicely scalable because we can use the same level 2 system that we have in maybe less equipped cars and add safety monitor and fallback range. So it would be quite scalable. We of course check all the ISO 26262 related aspects and also SOTIF. So more from the perspective of the architecture, is the architecture supporting SOTIF or not? And before I go on with the ISO 26262 traditional aspects, let me spend one slide on SOTIF related strengths and weaknesses of an architecture. I already mentioned it a little bit. An architecture can support a SOTIF argument, because we have these fault containment units, which can and shall be very much independent and diverse. So assume, as I already mentioned, the main AD is a highly sophisticated, complex algorithms. It uses end-to-end AI, and it calculates the trajectory. And due to the decomposition with the safety monitor, which can be by far more simple or robust in its algorithms, it only checks whether this trajectory of the main AD is not hitting an object. So it's kind of calculating free space and checking that you're staying on the road. And it's a very diverse approach. So by combining this diversity, edge cases are very less likely to be triggered compared to a maybe monolithic system. It is also good to approach AI faults due to this diversity. Also here, it's not that likely that you see the same hiccup on both ends at the same time. With a short excursus into SOTIF, let me talk about the ISO 26262 methodologies that we apply. So our systematic approach for analysis, having in mind the availability safety goal. I already mentioned we do an availability estimation of software and hardware. I will explain that on the next slides. We identify single point failures, components of identical kind. We do a dependent failure analysis, and we do a formal verification. We do all that based on one single model. So we have a database, and we derive all this analysis. We do ideally derive all this analysis from one central model. We are kind of tool agnostic in what we are doing, so we can work in any tool of the choice of our customer, but we also developed a framework in Excel that we are using for that purpose. We use that in series program. It's readily available. Excel has the advantage that you don't need licenses, etc. So we can work with that or in any other tool. And for the rest of this talk, I will use Excel screenshots for illustration purposes. If you know the icons, we do not apply all these methods on all levels, and this is depicted by the icons. For instance, the availability estimation and the formal verification, they are more suited for vehicle level and maybe for pairs of ECUs. So it's not that much suitable to do that within a single ECU for different reasons that I will explain later. Whereas the methods on the lower part of this slide, so identification of single point failures, dependent failures, and components of identical type, we also do on single ECU level. So that's depicted by the different icons. Some of those things you might say are not really new, and you would very well say so. Yes, they are not new, the lower part of this. So those three around the dependent failure analysis. We do that since years. We do that in traditional fail silent systems as well. But here we have to do it in a different way. We are now checking for availability safety goals. So the things we are looking for are different. We need to approach that differently. We need different checklists, etc., etc. So it's not new per se, but it's applied in a very much different context. Availability estimation and formal verification, to the contrary, are kind of new, or at least not widely adopted in our industry. Still, for availability, we believe that they can contribute to the overall system safety quite significantly. Maybe the summary of that quite lauded slide in a nutshell is that we combine quantitative availability estimates with qualitative analysis for independence with formal proofs of certain aspects and properties with the formal verification. And now we will look into each of them individually. And we will start with the availability estimation, failure rates in software and in hardware. And we know failure rates very well from random hardware faults, fit rates. But it's not really a thing in automotive industry to do that for software. And in my view, for good reason, because the ISO tells us that as long as we fulfill the processes, apply them correctly, the residual faults are contained. They are low enough. They are good enough. If you follow the process, it's good enough in terms of systematic failures for hardware and for software. And I believe that is a quite reasonable approach for the simple ECUs we had in the past. So not really simple, but maybe simpler than the ECUs we see now. If you compare classical brake ECU with an AD system, it's by far less complex. Also, the central compute entities we do have are way more complex now. And I put some screenshots here from a NASA study where it says that even an exceptionally good software development process can keep defects down to as low as 1 defect per 10,000 lines of code only. If we now consider these highly complex AD systems we have, high compute systems we have, we clearly will have a lot of software bugs, also in ASIL software. And that's why we believe that checking a combined failure rate of hardware and software can improve the overall system availability and safety. So we check raw fit rates, because diagnostic coverage doesn't help here. You need to check raw fit rates. And we do a sensitivity analysis for randomly triggered software and hardware failures, which are systematic in nature, yes, but they are kind of pseudo-randomly triggered by the input from the environment. And if you have strong diversity, different configurations, different algorithms, it's very unlikely that you will see some of them at the same time. So it's a kind of pseudo-random statistics. Maybe a disclaimer to that slide, please note, this estimates stochastically triggered failures. So a DFA is still very much essential to identify common causes and to ensure sufficient independence. How do we do that? A very high-level sketch on that slide. We start again with our data model, the database, the central one I introduced to you on a few slides earlier. So we fill the architecture, we reflect the architecture in our database to the level of granularity that is appropriate for the specific task, for the specific architecture and investigation. For instance, in an AD system, you might stay on that kind of level here. You have the main ingredients, the fault containment units, you have the main AD, you have the safety monitor, you have the fallback, etc. And in each of them, it's built up from different kind of partitions. So you have operating system and you have maybe some PMICs, etc., etc. But maybe you would like to stay on that level because you have to check a lot of ECUs, and a huge network of ECUs, which are in the end building up the autonomous driving system. So maybe you don't want to go into all detail of each individual device. But if you check, for instance, an X-bar and steer-by-wire system, you might want to check 2 ECUs in detail against each other. Then you really go down to software unit level. So it really depends on the architecture. We fill that into our database, and then we estimate the failure rate per component. On this upper half of this slide, we have the raw fit rates for the hardware. That's pretty straightforward. That's kind of exact results. So you check the databases, the standard ones, you check the data sheets, then you have these numbers. For the systematic failures in software and in hardware, it's a bit more complex. It's only what we call a quantitative sensitivity analysis. It's not an exact result. You need to kind of derive estimates for that. And we do that in two ways. We do that bottom up and we do that top down. I will explain that on the next slide. But for this slide, it's enough. So we have those different sources, systematic errors in hardware and software, raw fit rates for hardware, and we aggregate them per pass. And as we normally have two random pass, so a main pass and a fallback pass, and an AD system that can take over, we then calculate the overall failure rate, which is actually a Markov model because you need to check for a simultaneous failure. So the probability that the second pass fails within a certain time when after the first pass has failed, because they normally have the requirement for emergency operation or an MRM for maybe 2 minutes, 3 minutes, 5 minutes. And so you need to calculate the probability that within such 5 minutes, when you do an MRM, also the second pass will fail. That's a Markov causal, and that's what we do. And in more detail, for the bottom-up and the top-down data, so the systematic data, we collect reference data. We collect reference data from the software vendors we use. So if you use, for instance, a vector stack or a POSIX-based system, we try to get into contact with those and get field monitoring data, post-release field monitoring data from them. So how often have they seen failures, problems in the field per software version? This in the bottom-up area. And we also do a software complexity analysis. So we can estimate, we do have developed a methodology to estimate a worst case failure rate based on some certain criteria, which I will introduce you later. So this is kind of the two bottom-up sources. If we can gain data from the software vendors, post-release field monitoring, we will use those. If not, and/or we do a software complexity analysis. That obviously has a very, very, very low level of granularity. We do that on software unit level. The top-down data is OEM field data in this case of an AD system. So if we're in contact with an OEM, we ask them for the same things. So post-release field data, where do you have seen problems in the field for this certain technology, for this certain ECU, for this certain operating system, autosys stack, whatsoever. And that obviously will have a very high granularity. It will be DTCs, maybe it's DTCs for a certain functional domain, but it normally isn't fine granular. It's quite coarse. So we then cross-check those against each other, the bottom-up and the top-down data. For that, we aggregate the bottom-up data to the same level of granularity as the top-down data has, and we validate them against each other. And if they are kind of in the same order of magnitude, we take the worst-case assumption, so the worst one of those, and we derive the system availability rate out of that. If they deviate a lot, we of course try to find out what's the reason, and whether we are able to do so or not really very much depends on the data we can get access to. And that differs quite significantly. We do not reuse data, of course. It's always new data that we need in a new project because it's a specific project concept. So it really depends on how much the customer can provide in form of data. But in the end, we derive a sensitivity analysis and get an evaluation of the worst case scenario. We'll move on to the next method. Let me spend one more slide on that, as promised. How do we do this software complexity analysis? We do that on unit level. I already mentioned that. We do have a certain set of predefined criteria. So each software unit actually is evaluated against the same set. We then combine the ratings, so we have different criteria per software unit, and all these criteria we weight, and then we aggregate them into one rating per software unit, so a non-availability estimate per software unit. We do that for all software units, and then we are on the slide I've shown you one picture before. This evaluation ideally is supported by quantitative data from the vendors, or if we can get access to the source code, we can do so on our own. you name them, cyclomatic complexity, how long is the software in the field, etc. Number of post-release bugs, who is the vendor, do we trust the vendor, is it an ASIL, a qualified software module, or is it a QM? Kind of criteria catalog that we predefined, pre-weighted, and that we then fill in an expert judgment, supported by either data we get from the source code or that we get from the vendor. And the objective of this is to provide a sensitivity analysis, so not claiming that this is an exact result, it's a sensitivity analysis, and it can serve as an additional rationale for a holistic safety analysis under real-world constraints. Max method on the plate, a very traditional one, so the dependent failure analysis. Here we obviously check for single point failures and components of identical types, which will end up in the dependent failure analysis. And as I already questioned myself, you might do say that conducting a DFA is standard, nothing new per se. And again, you're right. But first of all, you need to check now for the availability, the safety goal. And second of all, the systems are by far more complex. In the past, the systems we looked at were simpler, were smaller. In case of an AD system, you have many issues. You have sensors, you have complex compute entities, you have actuators, and you have many of them. You have supporting functionality, etc., etc. So it's a huge net of issues. All of them have SoCs, all of them have software, all of them have applications, all of them have operating system, all of them have PMIX, you name it. So it's very, very broad net of things you need to look into. And that's why a systematic approach is pretty much essential. And that becomes quite obvious if you look at that picture. So sufficient independence is mandatory, and you see that depicted here in form of this diagram. On the left, you have the main AD, so the main pass, the level 2 system in our reference architecture, and on the right, you have the fallback system. On the vertical, you have sensors, the compute level with perception, sensor fusions, path planning, deciders, you name it. And then in the end, you have actuators. And the problem statement that we address with the dependent failure is depicted on the right. So we need independence for the whole chain, sensors, ECUs, and actuators. So from bottom up to top down, all of that needs to be independent in the whole horizontal dimension between main and AD. And quite commonly, one finds homogeneous redundancy in hardware and in software. That's depicted by the color coding. So, for instance, you have kind of the same basis software, could have the same basis software here in purple on the compute level. That could constitute a component of common cause failure. You could have the same sensor applied on the sensor level. So the bluish ones, the light bright blue, on the sensor level, you use one sensor on both sides. You could have one actuator being used on the fallback and the main AD. So it can be on ECU level where you reuse stuff. It can be on operating level. You might have the same vendor of a classical Althusser stack. You might reuse applications. You might reuse or have the same Ethernet stacks on both ends. Flex, right? All of that. Network, operating system, software components, all of that in all combinations. It could also be a common cause failure if the same Althusser stack is being used on an actuator level and a sensor level. So you not only need to compare on each level, but also between the levels. So it's a quite complex thing to do. That's why we do that in a very structured approach. So TTTech's contribution to doing so is our experience and the structure we have given us in doing so, the guidelines we developed, etc. And we actually really doing that in serious programs for vehicle architecture, for vehicle architectures, but also for X-by-wire systems, pairs of ECUs or a couple of ECUs, but also within ECUs, mostly again ECUs relevant for failed operational system, but in some smaller projects or for failed silent process. We not only do that analysis, we also propose measures. So we developed a set of criteria, predefined set of criteria and measures how to judge whether such a system is sufficient independent and if not, what we can do about that. So it's not only the problem statement, we're not only looking into the problems, we also always provide proposals for measures tailored to fail operational systems, tailored to argue or support sufficient independence and availability. That's how we do that. I mean, it's a quite simple slide. We start with the input, whatever we get, and as I said, that's a lot. It's many ECUs, many operating system, many ingredients. It's switches, it's CAN transceivers, it's a lot. We fill the database, all that into one database, and out of that database, we automatically check for single point failures. So is one component being associated to both paths? We automatically identify components of identical type on the level of granularity chosen. For instance, if we have the level of granularity that we look into sub structure of classic AUTOSOURCE stack, so basically be it OS or be it COM, we check what the same COM module is being used on main and fallback in any ECU, and that will give us a flag, and then we have in the tooling a selection of different criteria, measures, evaluation scheme, how we can judge that. After we have done so for all of them, we evaluate this. Is it good enough? Is it sufficient? That's an expert judgment in a round of experts. We propose measures if not, and that might then influence the architecture again. So it's closing the circle, and we do that iteratively, but all in one tool, till the verdict is that it is good enough based on the extra requirements that we have derived. And it's briefly explained, it's quite simple, but in the end, it's very, very effort-prone and intensive activity to conduct such an DFA. But in the overall process, we know very well. So I will move on to the last method, the formal verification. Actually, it's a subpart of formal verification. What we are doing, we do model checking. And we can also call that failure mode encoding and automated effect analysis. So it's a kind of FMEA, extended or specialized approach to an FMEA, which helps us in doing so. With this model checking, we addressed the problem statement as depicted on that slide. So in general, fail operational autonomous driving architectures are characterized by complex functional dependencies. I believe I talked about that already a lot. By complex deployment to real hardware, and you see a state explosion. So this vast combination of everything, everyone communicating with everyone, gives you a state space that's not really cognitively treatable by humans. So we as humans, we can't really see all the problems in that. And there where computer-based analysis comes into play and helps a lot. So this kind of model checking can find potential unforeseen emergent behavior that we as humans likely will miss. And even a standard FMA methodology, very structured, very experienced, very well suited, is not really able to do so, just because the state space is just that huge. As I mentioned, we do that via a model checker, and by that we ensure system consistency and absence of single point failures. And actually, under the constraints taken, is considered to be a mathematical valid proof that these properties are fulfilled. We'll explain that a little bit more on the next slide, but maybe one short disclaimer on the left. This method is most suited, one could say maybe only suited, to higher level architectural aspects and analysis. So it's well suited to vehicle architectures, communication between ECUs, pairs of ECUs, logical interaction of functions in an architecture like a vehicle or so. But it's not that much helpful, at least in the automotive context, in what we are doing for analyzing software stack of one individual ECU. Because what you need to do, as shown here, you need to define your system model very well. And if you think of communication between ECUs, that is very well possible. So you have signals, you have services going between one ECU to another, and you define them anyway up front because you have different parties developing this, etc., etc. So you need to define this anyway on communication level between ECUs, on logical level, who is speaking to whom. And this you can encode very well in the system model. But you can't really do that for huge software, or at least very, very effort prone to do so for an ECU internal operating system. So that's normally what you do not do. Maybe unless you develop such a stack, you might do that. Model checking is used to qualify hypervisors, compilers, etc., but not for applying when using an operating system in an ECU. So that's why it's more for vehicle level and logical levels. You encode the system. You also encode the failure models. You say how a certain signal, a certain communication link or logical link can fail. Can it fail arbitrary? Can it only fail silent? So it's gone, but it can never be wrong, or it can be wrong, but it is consistently wrong. So each message of that signal will consistently be wrong, or can it fail Byzantine? So it can send kind of the same message with two different contents to two different receivers. So it should be the same content, but actually it's two different contents being sent to two different receivers. So all this you need to encode in the failure model encoding. Then you need to encode the property that you would like to prove. So for instance, there's always one correct and only one correct trajectory being sent to the actuators. This kind of properties you can specify. And then the model checker, a tool, we use the SAL tool from SRE International. Then the tool will check the whole state space for you, will search for violations of the properties you have specified. And if it finds a violation, it will give you a counterexample. And then you again can close the loop. So you check your specifications, you propose measures and additional requirements. In the example of a Byzantine failure, you find with this tool that Byzantine failures can happen. You then, in the failure mode encoding, deactivate Byzantine failures, and you need to raise the requirement against your system that certain measures are needed to be implemented to prevent Byzantine failures. A readback of the message, a forwarding of the message, different methodologies being possible here. But there would be then a new requirement for the system architects. Okay, you need to take care of this specific failure mode. And you iterate that as long as you get approved, so the tool is not able to find any counterexample. And these are kind of mathematical models, formal verification. This really can be considered to be a proof within the constraints of the definition of the system model, so the granularity, you can do that, and the failure mode encoding. That was quite complex. Maybe one simple example, the deployment view. So we show here, actually it's not that simple, but what we show here is logical blocks. So we have a fallback, we have the vehicle control, and we have the safety monitor, and they communicate with each other. And in this specific example, let's assume that the fallback and the safety monitor are deployed on the same ECU in the same partition. So we don't have a good freedom from interference for those two. And now what is depicted here, maybe I'll bring up the laser pointer. What is depicted here is that the fallback sent the faulty trajectory to the vehicle control. So he wants wrong trajectory to be executed in case it is in charge, and it sends the same trajectory to the fallback to the safety monitor. But the safety monitor is on the same partition, so it's also faulty. And it says, oh, fine, this faulty trajectory is actually correct. It sends this verdict to the decider level. And as the safety monitor is faulty as well, it could invalidate the nominal functionality. So we also have the main AD. The main AD is sending a valid trajectory, and the safety monitor says, no, that one is not good. In this scenario, faulty fallback sends a faulty trajectory, and the faulty safety monitor classifies the main path trajectory is unsafe, and the faulty trajectory is safe, the wrong trajectory, actually unsafe trajectory, will end up at the actuators. So a single point of failure in this respect, a common cause, a safety monitor on fallback sitting in one fault containment unit, not being encapsulated well, can lead to such a failure. And this is a kind of obvious example. For illustration purposes, the tool will also find any kind of race conditions, etc., etc. And it really searches the whole state space. By that, last slide. Let me move on to the safety consulting and what we are doing. I hope you already got a brief overview of what we are doing in detail. Maybe from bird's eye perspective, we're more active on the left side of the V. So we are very much active in the design phase. We develop safety concepts for our customers. We review their safety concepts, but not only with a list of findings, but really with a list of proposals, so in close interaction with the customers. We do also low-level safety analysis, either in the context I've shown you, or also on demand. Generally contribute to the rounds of our customers, so if you need an expert, we can happily join you. And we have robust academic justification for the validity of our concepts. So we are 20 years ago, spin-off of the university, and as you have seen, we are still in a strong collaboration with academia. So we are on state of art of science, let's say, as well. We do POCs. So if our concepts can or shall be validated, then we can do prototypic implementations to provide evidence that the proposed concepts work. That more on the software level, but we also do have an hardware engineering in-house. So if that ever would be a thing, we could also do that. We are a bit specialized around this safety methodology for level 4 fail operational system. That's not the only thing we are doing, as I mentioned, but we're a bit specialized in this. So we have a strong footprint in this aspect: formal modeling, sufficient independence analysis, Markov modeling, etc., etc. We also do fail-op training. So we do 2 days workshops with our customers, often in the beginning of a joint project, but also standalone. We all do that for single issues, for multiple issues, or for redundant systems like huge fail operational networks. We look into ISO 26262 safety processes, but we are also engaged on the SOTA side of things. And with this, I would like to thank you